Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver. Today we're going to be solving some problems using momentum and conservation of energy together, and then just a two-dimensional momentum problem here. So let's start with this first one. Here we have a bullet and a block, and the bullet's going to collide with the block, and the block and bullet are going to slide a certain displacement and then stop. You know how much they're going to slide. There is friction here, so we have some friction. We know that the final velocity of the bullet in the block will be 0 because it's going to be stopped. There's a certain displacement. The mass of the bullet in the block we know, and we're trying to find out the initial velocity of the bullet. Okay, so for everything, like we've said before, right, you want to, for the collisions, use momentum, right? For motion, use conservation of energy, right? So we kind of know more about the back end of this problem than the front end of this problem. We're trying to find out the initial velocity of this block, but we kind of know how far this thing's traveled and how much friction's there. So you could go ahead and just start here if you want to, but you don't need to. You can say, okay, I know that I can describe this collision in terms of conservation of momentum, so I know that the initial situation and after the collision, that final velocity of the block can be described this way. So you can write your equation down for the sticky, right? This is our sticky equation from our concepts video, where the bullet and block are separate at the beginning, but then the bullet and block stick together and have a final velocity, right? And again, we're trying to find the initial velocity of the bullet, which is this. So now that we have a functional equation, we can solve for that initial velocity of the bullet. So we know that in order to get that initial velocity of the bullet, right, we have all the masses. So in terms of mass, we have all the variables we need. We just don't have this VF, right? But we can say, hey, that final velocity we can get if I can kind of work backwards from my final situation, right, using conservation of energy. So we know work is equal to the change in K, and work is equal to force times displacement cosine theta. We have friction here. It's a non-conservative force. We know with non-conservative forces, we have to use work times the change in energy. In this case, there's no change in potential energy, so there's just a change in kinetic energy. So that's what we got to look at. We got to look at the this side will always describe non-conservative forces. This side will describe the conservative energy, non-conservative energy. And this side will always describe the conservative energy, all right? So just like with always, we take care of cosine theta first. We know that friction, right, is the non-conservative force here. Friction's always opposite, right? If I were to draw this, friction's always opposite of our displacement. We're moving that way. So friction and displacement are opposite. That's 180, cosine 180, which is -1, which again, it just gives the sign. So when we rewrite this, we write the force is friction. That cosine theta turns into the negative, and that displacement stays the same. We know that, right? And then we know that there's no final kinetic energy because the block and bullet have stopped, right? But they initially move with some type of kinetic energy after they're hit, right? Because that transfer of momentum to them and transfer of energy. And so we know we have this initial velocity, which is -1/2 mv squared. These negatives cancel out. And then we go ahead and solve for this V, which is what this equation is right now, okay? So again, we skipped a couple steps there, but you should be able to do that, okay? All we did was solve for V here, okay? Used all these terms, right? M is M1 plus M2, that's what that is. That 2 came up next to the friction, and then it's squared, so we got to do the cosine. So this initial velocity will be the final velocity for the momentum equation, or the velocity after the collision, right? So oops, I drew that to the wrong spot. So what we're trying to say is that this velocity, let me just point that at the wall, this velocity right here is going to be the same velocity that's there, that final velocity. So this initial velocity you solve for is the final velocity for the momentum. So then we take this and put it in there for a final equation. So the initial velocity will be, initial velocity of the bullet will be the velocity of the bullet and the block combination times m1 plus m2 divided by the mass of the bullet. Okay, so this is the final equation. This is going to be the velocity of the bullet before it hit the brick. So that's the answer to that one. Again, there's a theme here, all right? So this second one, we're talking about a bullet hitting a block. It's rising up a certain amount. So instead of this situation, we have a little bit different one, obviously. And so here, nothing changes is the idea, okay? Here we know the initial velocity of the bullet and the initial velocity of the block, right, which is 0. V1 is going to be represented in these equations as the bullet. V2 will be represented as the block. And then when they're together, they'll just have one velocity. We know the masses of the bullet and block. We want to know how high this thing is going to swing to. So just like always, for collisions, right, just like we said over here, for collision, use conservation of momentum. For motion, use conservation of energy, okay? So for the collision side, right, we know the bullet and block are separate, and then they collide and stick together and move. So initially they have their own separate velocities and masses, essentially, and then over here they don't. So the initial velocity of the block, which is V2, is 0, right, where the initial velocity of the bullet we know, right? So this becomes 0, and then the final velocity plus m1 and m2. This is, again, our sticky equation. Again, you can start with the full conservation of momentum equation and get to this, or you can watch the concepts video, right? This full conservation of momentum equation. Or you can watch the concepts video and see that you can just use this equation. If you can remember, this is what we call the sticky equation. So once we know this, then we want to go ahead and solve for final velocity. The reason why we want to solve for final velocity is we can use that final velocity in our initial kinetic energy over here to see, again, how high the block is going to go. So we solve for final velocity, okay? And again, we say it right here, this final velocity would be the initial velocity for kinetic energy when the system begins to move, all right? So we need to then get an equation for our height so we can substitute this velocity in. So again, to describe the motion of this object once the bullet and block collide, we use this. We start with initial kinetic energy, initial potential energy, final kinetic energy, and final potential. We know there's no initial potential energy in terms of reference height, but it is moving, so it has kinetic. We know it stops moving once it reaches this height, so there's 0 kinetic energy, but it has a final gravitational potential energy in terms of reference height. So that we know there's an initial kinetic and a final potential. These two terms drop off, and we expand it out. 1/2 v squared equals mgh. All right, the masses will cancel. You get this equation, and then we want to solve this equation for height because we want to know how high it's going to go. So we solve this equation for height, which is this, and then we take our final velocity that we solve for over here and pop it in there for v squared. So you can see that this is the final equation for height, bringing in this velocity, this final velocity that we found once the block and bullet hit, which became our initial velocity over here in this equation in order to get the height. Okay, so again, we said a lot of things in both these really fast. The nice thing is this is a video, right? So you can go back and listen to what I just said a gazillion times. Rewind it, listen to it. What did Carl just say? Rewind it, listen to it. I didn't catch that part. What did Carl just say? He's saying it too fast. Well, then slow it down, rewind it, listen to it multiple times until you hear it, because I'm speaking slow enough for you to hear it. It's just a lot at once. Okay? So these are two situations where we're using energy and conservation of momentum, okay? I want you to pay attention to this because I'm going to try to get to another video, but in terms of using non-conservative forces and conservative forces, or non-conservative energy and energy together, where we'll use this equation again, but until then, this is your example for using non-conservative energy and conservative energy together in order to solve. So anytime you have non-conservative forces like friction, something losing heat to, friction loses heat to entropy, or drag or something like this, where all the energy isn't used in the system, that's non-conservative, and that's why we use that. Okay, for this final one, this is a two-dimensional momentum collision, so we're not worried about energy and momentum, we're just worried about momentum here. All right, so we have these two balls, or hockey pucks. This puck is moving with a certain velocity, and this puck is stationary. They're going to collide, and then they're both going to shoot off into two directions. So this is what we call a two-dimensional conservation of momentum, or two-dimensional collision problem. Okay, and the question's asking for V2. They give us everything for V1. They say, so when these things collide, V1 shoots off in this certain velocity, 0.36 meters per second, at an angle of 37 degrees. We want to know what V2 is going to do. We want to know the angle that it shoots off of, or the direction, and we want to know its final velocity. But keep in mind, we were just given the terms for V1. We don't know anything about V2. So that means when we solve these equations, we need to solve everything in terms of V1 because those are the only values we know. So that's the thinking you have to bring in here, okay? Yes, we need these values in terms of V2, but we can find them in terms of V1. So the first thing you have to do for two-dimensional problems is you have to go ahead and you have to look at x and y components, right? You just can't look at one momentum equation like we've kind of been doing where there's just one dimension. If you have two dimensions, you're going to have two momentum equations, both describing the momentum in the x and the momentum in the y, all right? We were also told that these two pucks have the same mass. So when we write this equation out, the same numbers in every term, even though they're essentially different masses, so they cancel out and we end up with just this equation. Same thing for the y. All those masses are the same. So the masses cancel out, we're just left with velocities here, which is good because we're looking for a final velocity. All right, so when we do that, when we cancel out the masses and then we also include the zero for the zero velocity for this initial situation, we see that this velocity drops off. We're just left with the initial velocity of the puck that's moving at the beginning. And then we're left with these two velocities. That's not initial, that's one, sorry. We're left with these two final velocities, V1 final in the x and V2 final in the x. Now, remember, we're trying to find V2, but we only have V1 values, right? So I solve this equation for V2, bringing all my V1 values on this side. I know all these numbers, right? I know V1, it's 0.36. I know theta, right, which is 37 degrees. So if I know these two numbers, and I know the initial velocity of V1, so if I know these numbers, then I have a final equation. I know V2Fx because this is 0.45, this number right here, right? I should probably, right? This is 0.45. This V1 is 0.36, and this theta, right, is 37 degrees. So you know all those numbers, so you can get F2F of x, which is what we're looking. We're looking for the x component of F2, right? We're looking for the x component of V2 and the y component of V2. And we're finding it in terms of V1, right? We know these numbers, and they equal to V2x. All right? Then we do the same thing for V2y, right? We just said the masses cancel out. In terms of y direction, for both of these objects, they have zero velocity in the y. This one's just moving in the x initially, and this one has none. So that means both sides, right? The velocity in the y for the first mass is zero because it's just moving in the x, and this thing's not moving at all. So they're both zero, so we make that whole side equal to zero. All right? And initially we cancel out our masses, so we're just left with velocities on both sides, and then those velocities we know are zero, so this becomes zero. Don't forget that way the masses disappeared because they're all the same, they cancel out. And then we're left with just this side where you have V1F in the y. I should have put that in V2F in the y. Now again, we need V2F in the y, but we got to find it in terms of V1, and that's what this is letting us do. This is equal to 0. We can just bring, right, V2F over, right, since it's a negative, we'll make it positive, and we can see V2F is equal to V1F, where V1F is V1 sine theta. So we know V2F is equal to V1 sine theta, where we know these numbers. Again, I probably should have written these in here, where V1 is 0.36, and this theta is 37 degrees. So we know both these numbers for V2F, right? So if we have V2YF and we have V2XF, we can use Pythagorean theorem to get V total. To get this V, we got these two components now in terms of V1, and we can use Pythagorean theorem because it's a right triangle to get V2. So that's what we do. There's V2x squared plus V2y squared, and then we know V2x is this equation right here, which is V1xi minus V1 cosine theta. Again, I have all the numbers there for you so that you know what's going to go in there. So that's the first equation, plus Vy, or V2Fy. which is just equal to V1 sine theta. Put that in there. Again, they're squared because of Pythagorean theorem. You put the numbers in there and do the square root, you're going to get the number for V2 total. All right, now we need the direction, the angle that it's going to, right? Well, we know tangent theta helps us solve for that, right? Where it's opposite over adjacent. We know that the opposite is going to be the y, the adjacent is going to be the x here to that angle. That's how we write it. But again, we just know we're using V2y and V2x in terms of V1 though. So when we write out the equation, right, we want to bring over tangent, do the inverse of tangent. And then when we get our final equation, theta is going to be equal to the inverse of tangent. And then it's going to be V2y, which again is this, right? Oops, do I have those written? I believe I do. So let's just reverse this because I see what I did. So we want V2y on the top, right? And V2y is this right here. So we want to write that V1 sine theta, where we know that theta, right, is that 37 degrees from over there, right? We know that V1 is 0.36, so we know those numbers, right? And then the bottom is going to be this one, right, which is the V1x minus the V1 cosine theta, where again, that theta is again 37 degrees, and you know all those numbers. Again, the numbers are here, right, 0.45, this one is 0.36, and this one is going to be 0.36. So those are the numbers that go in there. So there you go, okay? Again, there's everything you need. That's the direction it goes. So that's how you solve a two-dimensional momentum problem. There's a lot here. Go back and listen to everything I said here, why we solved it the way we did, okay? Because I found V2xf and V2yf in terms of V1 because that's what was given. So watch that a lot because this is a complicated one. And if you can follow me and start to understand what I'm saying here after you've watched it maybe 5 or 6 times, awesome, because you're going to need to watch it 5 or 6 times to really understand. But look at this work. Stare at the work that I did. Look at what I'm doing here. Look at what I'm doing here. And look at what we end up here, right? Just keep in mind that down here, this is like the final work, right? Those 2 steps above are getting the components, and this is getting the total velocity for V2 total, all right? Thank you so much for watching. I hope this was helpful. Like I've been saying, watch it again. Super proud of you. Keep up the good work, and I'll see you on the next video.